Okay, so it's my pleasure to introduce Richard Murray for the third keynote of the program. And Richard is going to talk about a rapprochement between formal methods and control. And Richard is from Caltech.
Great. Thanks, Claire. I'll tell you that this is Claire's title, not Richard's title, which you can tell because I would never use a French word in my title. But so it's pretty obvious that her Canadian background, she's trying to be balanced and make all those things. Okay, but it's a pleasure to come and talk and to come back and to get to see everybody and have a lot of fun. A number of us have been putting up quotes that we can remember from Shankar, so sorry, Shankar, but I'll give you one of mine too. And I remember this, very explicitly. We had just had lunch at Aki, and we were coming back, and we were standing outside Corey Hall about to go in, and Shankar said, "Richard, computer science, this is all organized hacking, isn't it?" Right? In this way, he asked me, I'm like a second-year graduate student, right? What the hell do I know about this, right? Anyway, now here's the dean of engineering, right? I want to make sure this is on YouTube. It's going to be broadcast, right? So computer science is organized hacking. Shankar Sastry, circa 1998, right? Outside the door of Corey Hall. For a long time, this was my view of computer science, right? It's just all organized hacking. There's no mathematics. You've already heard this from multiple people. Of course, control theory is not necessarily much better. So John Doe, my colleague, said control theory is impenetrable mathematics, right? Sort of how can you make PID so hard that nobody except somebody with a PhD can actually understand it? This is what control theory has become. So I don't know that we're doing much better. And this was in the context of writing some things about future directions in control. And so today I want to talk about something maybe at the intersection of these two things. So I decided to do that, and so I'll talk about impenetrable hacking. And I thought this was good because Stephen, of course, gave a talk yesterday about organized mathematics, so really there wasn't much left to talk about, so I had to choose the complement of this. What I hope to tell you about a little bit today is how do you make hacking something that you can't even understand without a PhD? And so that's really the goal of my talk today. Okay, so just in case you get lost in the middle or tired or start doing some other things, let me just tell you what I'm going to tell you about. So here's an abstract for this talk. What I really want to try and get across is that I think we need to do a couple of things. So one is we really need to think about how to get control theorists, right, so some fraction of us in the room, to be able to read this formula. All right? So unfortunately, Shankar taught me many things, but he didn't teach me how to read this formula, right? And so just, how many people could read this formula aloud? Okay, good. So I want to come back, right, a couple of years from now and have all of you raise your hands and say, because you're at Berkeley, right, you know how to read this formula, right? Because I think this is an important set of mathematics that computer scientists have developed, right, that is very important for what control theorists are going to do. Now, on the flip side, I think that computer scientists should all be able to understand this diagram, okay, and what it means. Okay, so how many of you understand this diagram and what it means? All right, good. All right, so now, as a community, we've got to do both, right? We have to speak to the computer scientists and tell them why is this diagram down here on the bottom important. But we also have to think about how do we educate ourselves and our own community in terms of how the top diagram is important, or the top set of formulas is important. And so what's interesting to me about this formula and this diagram is they actually say the same thing. All right? And so what I want to talk to you about in the talk today is, why is this actually the same statement? Right, essentially written in two different forms, right, at some level of abstraction, right? So it may not be evident. Hopefully at the end of the talk, it'll be a little bit evident about really, these are basically trying to solve the same problem, right, and they're sort of saying that the same way. Okay, so let me just say a little bit about control theory and a little bit about formal methods in terms of, how I think about those two things, and then I'll try and put the two together. If we think about control theory, so control theory is something that many of us, learned when we were sort of here at Berkeley, and historically, right, control theory has been how do we take sensing, actuation, and computation and connect these things together in a feedback loop. This is an example of a complicated control system. This is an autonomous vehicle that some of the students at Caltech developed, some of whom later came up here to graduate school, including Jeremy Galula and George Hines and Hao Miao H, who worked on this. And certainly, the origins of our field over here on the left were very much about how to do this and how to think about providing stability, performance, and robustness for these very complex systems that we were designing at the time. But I think as we've gone on in the field and sort of looked at the types of problems we want to look at, we started to look at much more complex systems, right? Autonomous vehicles are still there, control of the cell, control of network systems and other things, control of very large-scale enterprise-wide systems, whether those are for military applications or other types of applications, and how to think about dynamics, interconnection, communications, computing, and software all in some sort of a unified framework, right? And I think that's one of the things that here at Berkeley was very evident, in things like the integration of EE and CS and the way that's done, and the things that Shankar taught us as we were learning controls and robotics and all of these other things. And I think there are a couple of key principles that come out of control that are very important for thinking about design of complex systems. And so one of those is that we can use feedback as a tool for managing uncertainty. So how do we use the ability to sense what's actually going on to mitigate the uncertainties, right, of the dynamics or the sensing or the disturbances or other things that are going on? A second is, of course, we can use feedback to design the dynamics of a system. And so we can change what the natural dynamics are by integrating these into feedback systems. And the two of these together, one of the very important things they do for complex systems is they give us some notion of modularity, right? That is, we can design the dynamics of a component to be robust with respect to what's connected to the component, to changes in the component, and this allows us to build some of the sort of sophisticated complex systems that we do. This is how we get, or one of the ways that we get complexity at scale. So I think that this is really, to me, what control theory is about, and you can see already, right, that it has lots of overlap with the problems that people in computer science and many other disciplines are trying to solve. Now, on the computer science side, what is formal methods about? Since that was the title that Claire gave me, I decided to say a little bit what it is. And so in formal methods, we would think about having some system description, now no longer in a continuous time, continuous state, or even continuous discrete time, continuous state, but rather a discrete state space, a finite state machine, for example, that would describe our system. Right? What are the sets of modes that our system can go through or something like that? We would have some sort of a specification written here in this cryptic language of temporal logic. And so I'll say a little bit more about that in a second. And then what we want to do is we want to say, does this system satisfy this specification? Right? And so this system might be something that I designed, and I want to make sure that it satisfies some specification. And so we want to try and capture both what the system is doing, but also what the environment is doing. I'll say more about that in a minute. And the formal methods community, now going back 30, 40 years, has spent a lot of time thinking about the mathematics of this, but also thinking about algorithms to do this, and in particular coming up with a framework that allows us to answer this question. And that framework is captured in the context of thinking about searching for executions through this discrete state space that violate the specification. That is, if I could find a counterexample for you, right, here's your spec, but here's a sequence, right, that I can go through in this diagram that actually violates that, I've given you useful information. Right? And if I can't find such a sequence, if there is no such sequence, then I satisfy the spec. Right? So that's the idea of model checking. And so there's a way to do that. And this is the mathematics of formal methods, in some sense, or at least the model checking part of formal methods, where we have this system, we have some property, we negate the property, and then we go through and search through every possible execution of this system and ask, is there any way, right, that I could satisfy the negation of the property? And if I can find such a thing, right, then I have given you a counterexample, right? And so as an engineer, that's great, right? Because somebody says, this isn't going to work, right? You say, of course it's going to work. I designed it. I'm great. I know how I'm going to get it to work. You say, no. Look at this specific sequence of things. If this happens, followed by this to this, you're going to end up here, and you're not supposed to. Oh, crap, you're right. Okay, now what do I do, right? Now, of course, the challenge is you got to search through all possible executions, right, in a discrete space. And of course, one of the things that this is very useful for, particularly in these complex systems, is when things aren't executing all synchronously, right, in one processor, right? If I've got multiple things and they're running in different processors and there's all sorts of different interleavings, that's where we get into trouble, right? This happened, but some other processor wasn't looking right then, and I got two different events coming in two different orders to two different processors, and they reacted wrong, right? At least that's where a lot of our bugs come from. And so model checking is a tool that can help us deal with that. Okay, so model checking, I think, is something that's quite useful from that point of view. And the formal methods community has now gotten very good about thinking about model checking. It will check all possible execution states, including worrying about interleavings. Modern model checkers can check quite a large state space, 10 to the 9th, 10 to the 11th discrete states. So really they can go through very large states. They do that by not enumerating all of them, but by representing them in other forms. So binary decision diagrams and other things, for example, allow us to reason as Lyapunov functions do, right? Reason about a large set of states without writing them all down explicitly, right? So think about a representation in which I can say all states contained in this set will move to this set. That's a Lyapunov function or barrier certificate, all of these types of things. Same type of idea, right? So same sorts of things coming up. And so in the context of formal methods, one really wants to think about how do we leverage all of these advances for doing system and control design. And so I want to tell you a little bit about some ways I think we can connect these two things together, and that they have been getting connected together. And so the rapprochement of this is that they have been coming back together. They're trying to solve the same problems. They're really kind of coming together, I think, in an interesting way. Okay. And so I want to talk about that in the context of controller synthesis. And so here we have a control system, and so in this control system we have some process dynamics, we have some unmodeled dynamics, the E that we normally put as a delta block up there, if we were taking 221 or whatever the current course number is. And then we want to design a controller such that some performance specification is satisfied, right, under the unmodeled dynamics. And now what I want you to think about is, if these are not linear time invariant systems, but rather finite state machines, right, what does that problem look like? And so we can think about this as, given a finite state machine that describes my process dynamics with possible actions that I can take. If you think about autonomous driving, I can drive straight, I can turn left, I can stop, I can change lanes. These are all discrete actions that I can take. You think about the environment similarly as some set of possible behaviors that the cars around me can take. Car can stay in its lane, it can decide to come into the intersection, turn left, turn right, do all of those things. That's a bounded set of behaviors somehow, right? It interacts with me, so when I do something, it does something back, so it's a feedback interconnection, right? It's just not an open loop thing, it has to, depends on my action. So I think this is the right diagram. And now, if we were a control system, we would say, great, if you give me x dot equals ax plus bu, and you give me the environment as some norm-bounded delta, right, then I will synthesize for you, H-infinity synthesis, LQR synthesis, your favorite method, a controller that automatically satisfies that. So what does that look like if these are finite state automata? And I guess the first order answer is, it looks terrible. All right? That is, you can pose this problem, but it's doubly exponentially complex in the size of the specification. All right? So we're kind of screwed, right? Because if I gave you a specification that was 5 long, that's 2 to the 5th, right? So that's 2 to the 32nd. Let's suppose we could solve that problem, right? That we could solve it fast enough. We could solve something in size 2 to the 32nd. I then say, yeah, but it's more complicated than that. There are 10 specifications. It's now 2 to the 2 to the 10th. That's 2 to the 1000th. Okay, so now, it's the end of the universe, and we still haven't solved the problem, right? And so, of course, one answer for why nobody does this is it's too hard, right? This is just an intractable problem. Right? And in general, of course, it is an intractable problem. But there was a change that occurred now about a decade ago, which is that people started to think about, well, it's not like we solve fully nonlinear control problems that aren't even Lipschitz, et cetera. We restrict, right? We say, look, we're going to look at some subset of those systems. And there's a very nice subset of systems in this context that Pitterman, Pinelli, and Sarr sort of worked out some nice results on, called GR1, Generalized Reactivity Formulas. And in the context of GR1 formulas, and I'll show you what these look like in a second, it turns out that the results can be much better. And in particular, we have to make some changes in the problem setup. So one of those changes is that this is, in some sense, to be thought of as a game, right? The process is in some state. Now what's going to happen is the environment's going to choose an action, and the controller's going to choose an action. And in principle, these are simultaneous, right? And then we implement those and see what happens. We're going to break that symmetry, and we're going to do now a 2-player game in which the environment chooses an action, tells the controller what it's going to do, doesn't change its mind. The controller chooses an action, right? And then we both implement these actions. All right? Now, you can say, well, that's a dumb assumption because that doesn't really happen, right? But if you're computing fast enough, this is not terrible. Right? So if you imagine, we're going to do this in the context of traffic, and somebody says, okay, I'm a car, right? I'm, the car coming in the other direction. I start to change lanes, right? Then I'm going to assume that for the next, say, 100th of a second that it's going to continue to change lanes, right? And then I can go back and look again, right? So in some sense, it's just the fact that if I'm looking quickly enough, I may as well assume that what I saw it doing, it's going to continue to do for that short period of time. And if it changes after that, that's okay because I'll get my turn again, right? So if we're running fast enough, this is not a terrible assumption, all right? So I'll claim that this is not unreasonable. And once you do that, then you really change the way that you think about the system, because now in some sense you can say, okay, look, I can kind of unwrap this, right? What happens is the environment chooses an action. The controller sees the action. It knows what the current state of the process is. It then decides on its own action. We now implement those 2 actions. The process does something once those have been implemented, and now we start over, right? And so now the environment, knowing what the new state is, chooses an action. The controller sees that action, right? We implement those, et cetera. And so I can unwrap this, and you can imagine saying, okay, good, so now what's the problem I have to solve, right? I have to think about, if this is what I want the controller to do, then how do I make sure that no matter what the environment does, I have some action I can take, right, that forces me back into this set. It's like a Lyapunov function. I want to stay in this set. The disturbance might take me out. Can I bring myself back in, all right? In fact, it's exactly like a Lyapunov function, right? Except we're in discrete spaces, right? And so these are now sets that we have to represent differently. But it's really the same idea. Okay, so if you do that, then it turns out that you can solve these problems in a fairly efficient way. How efficient? Cubic in the number of states of the underlying system. Cubic in the number of states, wow. That's like a lot better than doubly exponentially complex, right? That's like doable, right? So now I should tell you I'm lying. This is all things. Because, of course, what's the number of states versus the number of specifications, right? Well, in fact, it could be exponentially hard. The number of states could be exponential in the size of the spec. But often it isn't, right? It could be worst case, but often, and by the way, we control the specifications, right? So we can choose, right, which things we want to specify to some extent, right? We have to map what we want this problem to do. But in our experience, many of the times, the number of states to describe what we want it to do is not terribly high, and so we get something where the number of states is reasonable. And so now we can actually synthesize these things, and I'll show you how that synthesis works in a minute. But we can only do it for this subclass of systems. So what's this class of systems look like? It looks like this. Okay, so here's another cryptic formulas. Today I'll read it for you, or this time I'll read it for you, right? A year from now, I'm not going to read it for you. You have to be able to read it. Right? Okay, so the specification says that the superscript means environment, the superscript, or the E superscript means environment, the S superscript means system. And this says that assuming that the environment satisfies some initial proposition, and always it satisfies some safety conditions. Right? So if you're imagining driving, I'll say, for example, I'm going to assume that cars always stay in their lanes or that they satisfy the laws of physics, right? Sort of things of that sort. And always eventually some progress condition is satisfied. This is a liveness assumption, right? This says that something happens over and over and over again. This proposition, whatever it is, right, must be true in the future. So this means eventually. So eventually this property is true. Some point in the future it's true. But the always eventually means it's always the case that it will be true in the future. So if it was true and then it went false again, it's going to become true again, right? So this says that over and over and over and over, this thing's going to become true. So now under the assumption that the environment satisfies these conditions, and these conditions can depend on the system state as well. They are the environment's description, but they are interacting, right? So the environment gets to see the system state. That should imply that the system satisfies some initial condition. That's a technical thing, doesn't really matter. The system has some safety requirements. I'll always stay at least 1 meter away from all cars that are near me, right? And I will have some liveness condition. I will always eventually do something. I'll always come back into the proper lane of travel. I'll always eventually go back and get gas. I'll always eventually, right, you know, sort of arrive at whatever spot if I'm a bus and I'm going around or something like that. So this form of specification says that safety plus liveness of the environment should imply safety plus liveness of the system. And you can, although some things may not be obviously in this form, they often be encoded in this form. So for example, we can do reactivity, as you might imagine. If some event occurs, then I should respond to that event in the following way, right? Can be encoded as a GR1 specification, for example. And so you have this idea that you have these environmental assumptions and you have this system guarantee, and this is the specification. And this is a very useful specification format, right? This is one particular language. There are many other languages. This one is in linear temporal logic. There are other types of temporal logic. There are other descriptions, omega regular automata, other things. But they're all kind of equivalent to these ideas, or at least they're there. And so again, right, we have this general reactivity formula. It also is in an assume guarantee format. Right? We should be used to this, right? Because we make assumptions about the environmental disturbances, right? I have some disturbances, they have some norm bound on them, right? I mean, or I want the output be linear in the size of the disturbance, right? So that's some assumption about what those disturbances must look like. And then under those assumptions, I'd like this guarantee to hold. What happens if the assumptions are violated? No guarantee, right? Okay, we're used to that too, right? What happens if that norm on that delta falls outside? I can't guarantee stability anymore, right? So there's always a gap, right? And we have models, right? We have specifications, right? As good engineers, we have to sort of deal with that gap. We can't put everything in this formalism. But this allows us to synthesize a controller that satisfies this specification. So correct by construction synthesis, just like LQR, H infinity, or any other technique that we know, right? Except here done on these discrete state spaces. Okay, so that in some sense is what the formal methods community has figured out how to do. And again, I think that this is very much aligned with the way we think about control systems. Okay, so I I'll call this hacking in the sense of, how might you solve this, right? You might just sort of say, oh, I just, hacked together some controller that actually I claim satisfies the spec. I model checked it, right? Some black box thing, right? I applied it, I model checked it, okay, right? But really, I think that there's a beautiful mathematics associated with this as well. So this is the impenetrable part of the talk. So this is the problem that you need to solve in order to do synthesis, okay? This is like writing a linear fractional what is it, a T in LFTs? Yeah, an LFT for something, right? It's like nobody understands it anymore, right? So, like, what the hell is nu and mu and that symbol? Do I even know how to write that in LaTeX, right? I mean, you're in trouble, right, if you don't know, like, what to write down, right? Okay, but nonetheless, what this is actually describing is, so let me tell you in words, right, or in gestures, what this formula is trying to do. And it's roughly the following simple idea. Let's suppose that I can find a winning state for my system, right? So a winning state meaning I can find a trajectory, think of it as a periodic trajectory that satisfies my system spec, right? And I say, look, I know that in this really simple thing, it's a dumb trajectory, it's not, taking into account what the environment is, but if I just do this, right, then I will satisfy the spec, right? And then I can say, good, now what can the environment do? And if I say, here's a set of states that I know satisfy my spec, can I find a set of states such that in this bigger set of states, no matter what the environment does, I can find a reaction that takes me back into this winning set, right? So that means that I'm going to grow the number of states. I'm going to look for the states that are bigger than this, such that if the environment takes any action, I can take a counteraction that brings me back into this winning set. Call that the next bigger winning set, right? Iterate. Do it again, do it again, do it again, do it again, right? Keep growing this until it stops. When it stops, right, you have hit the largest set of discrete states, right, in which there exists some strategy, right? And that strategy is easy to articulate, right? Because you know from this set of states that for every action the environment takes, right, there exists an action that brings you to the next smaller set. That's your control law, right? So that's really the way that we can construct these control laws. And it turns out if you go through these formulas and look at this, that can be done in a complexity that is cubic in the number of states of the underlying representation of the system. All right? So that's what all of this is saying, right? But there's a very beautiful mathematics associated with this. It's as beautiful as differential equations and dynamical systems and Lyapunov functions and other things, as rich mathematically, as impenetrable, right? So the control theorists, we should all be happy, right? We can now make it so nobody understands what the hell we're doing. But you can write algorithms that solve this, right? Just like people write algorithms that solve control problems, and engineers go off and use those, even if they couldn't necessarily prove everything in detail about them. Okay, so I hope at least you see that there is, some ability within this to solve problems. They still, the complexity, there's still lots of open challenges, etc. Let me just give you an example of the type of problem that one might solve. I'll do this driving example. Where here the specification is something along the lines of the following. I got these two little stars over here. Let's suppose this is the Berkeley shuttle, right? And it needs to stop at the corner of Hearst and Gailey and down by the BART station over and over and over again, right? That's the spec. So what do I want to do? I want to always eventually go to here and always eventually go to here, right? I want to stay in my lane, right? All of those things. So I have some specification, right? So I might want to do things. I shouldn't collide with other vehicles. I should stay in my travel lane unless there's an obstacle around that I need to go around. I should only go through an intersection when it's clear, right? California Driver's Handbook, right? Write all those things down. All of these can be encoded in as GR1, well, in linear temporal logic. I haven't even gotten to GR1 yet. I need some assumptions, right? So here are some assumptions, right? I may say an obstacle can't block the entire road, right? Why? Because if an obstacle is blocking the entire road, I probably can't proceed without violating the law, doing a U-turn in the middle of an intersection or something like that, right? At a higher level, I might deal with that, right? But I've got to put all of these in, right? So, of course, as is usual for engineers, all we're really doing is changing the problem from you designing the control law directly and having to be really clever to you designing the specification so I can call an automated tool to design the control law for me. Now you got to be really clever, right? You got to know what these are. Good news is, if you write down a set of system rules and environment assumptions, and they are not consistent, when you try and synthesize it, will say there is no such strategy, right? If it says there is a strategy, right, it will find it for you, right? So you're sort of guaranteed good, right? If you find one, it satisfies it. You still have to make sure this is really the right set of assumptions that you wanted. And this typically is an iteration. You write down a set of assumptions, try and synthesize. It says, no, that won't work. So for example, here we say we only proceed through an intersection when it's clear. Down here you'll see one that says each intersection is clear infinitely often, right? Why? Because the first time we did this, we didn't put this assumption in, right? And the synthesizer came back and said, aha, but what if a car stays in the intersection forever? Then you can't satisfy your spec, right? You say, oh yeah, well that's not reasonable, right? You know, of course, obviously, right, the intersection has to be clear, right? So how do I say that? Always eventually intersection clear. Ah, okay, good, that's in my format, right? Okay, so we can do that. It's exactly this sort of a game. The specification, these are all finite state automata. The specification is exactly this form, right? So we can actually synthesize these things. This is what a simulation of a synthesized controller looks like. The red things are obstacles. As the obstacles come up, right, we go around them. We come to an intersection. Eventually, it must be clear. When it's clear, we'll drive through the intersection, right? All of this was synthesized automatically. All the logic that's controlling this. There's a controller that's doing trajectory generation and other things also, right, sitting on top of this, right? But we're going to go around and come around, right? And we're going to say, okay, intersection's clear, so I can go around again, right? So I do all these things. I come here, it's blocked off. I change my rules, right? Because I say it was blocked, right? So I turn around, I do other things. So all of these things can be done and synthesized, and it's all rigorous, right? And it's all guaranteed to be correct up to the models that we wrote down. Okay, so that's kind of what I wanted to tell you a little bit about. So maybe let me just try and summarize this then. For us, this is a very natural control system to write down, and we can think of that control system just written a little bit differently as looking like this. I want you to think about the fact that this is exactly the system that I just solved, where these are now finite state automata. And here I've just split up my E and my delta a little bit differently because I did the chart a little bit differently, but it's exactly that same idea. And of course, what's the spec that we might satisfy over here? Well, we might say something like, for all delta norm bounded by 1, the output should be norm bounded by the, or should be related to the norm bound on the input, right? What's the spec over here? Well, it's exactly the spec that I've been writing down. So this is, of course, an environmental spec implying a system spec. Over here, the environmental spec is, right, that the size of the 2 norm of D is the thing that I care about, right, and its relationship, and that my norm bound, I have some norm bound on the uncertainties, right? So that's a description about the uncertainties, the environment. And then I have a system spec, which is that I really want this inequality to be satisfied, right? I'm specifying the behavior of the system. And of course, over here, it's the same, right? Here's my environmental spec, right? This is what the environment can do. Here's what my system spec is, right? And so really, it is exactly that same format. So again, I think that these really are very compatible ideas. The notion of finding these fixed points, right, or fixed sets in this algorithm are things that relate to different ways that we can do control computations and other things as well. So I think there's a richness there that can still be done. Okay, so this is stuff that we've been working on for a while. Other people have been working on for a while. I think it shows where the intersection of computer science and control theory has some benefits. I think it's not the only one. I think there are lots of places where we can look at the intersection of computer science and control theory. So think of these as mashups, right? You know, how can we put a couple of things together? And I showed you today a little bit about formal methods mashed up with robust control. And so if you think about it in this way, I think it's interesting. Security and privacy mashed up with controllability and observability, right? So like George is working on that, right? I mean, this is, you know, that's clear, right? I mean, these are the same ideas, right? In some sense, right? But different mathematical frameworks. But if we think about, you know, what do we mean by security? We mean that, you know, I can't make your system do something bad. What do we mean by controllability, right? That I have complete control over what I can tell it to do, right? I mean, they've got to be related concepts. So how do we put them on a similar mathematical basis? Clearly, machine learning and system identification and adaptive control, exactly the same, you know, issue, right? I mean, these are obviously, right, sort of related to one another, and people in the online learning community are rediscovering things about, right, adaptive control, right? And so, but the mathematics is different, so how do we sort of say this at a higher level of abstraction where we can say, it's the same concept, right? You're just looking for this thing, which is the same as this concept, and here's an insight over here, right, that gives you something new, right? Because that's, of course, what we eventually want to do. I think there are lots of other ones, many of which we've already heard about. IoT and network control systems, HCI and MICA, or HCPS if you want. So MICA is the worst named program that Shankar is responsible for. Mixed initiative control of automateams. Automateams, what the hell is that, you know? So, you know, it's definitely an acronymized thing, right? We need an A, what can we do, right? Receding horizon control and model predictive control, right? You know, those are the same, sometimes in the same domain, right? But I mean, that's what people are doing, right? Online optimization and all of these things. So I think that there's a lot of opportunity to do more here. I think that, you know, Shankar's been somebody who has, over his career, once he got past the sort of organized hacking comment, kind of recognized that computer science might have some value. And I think in the rest of his career after that, you know, the fateful day in 1988, he started moving down the right path, and so has given us lots of things to think about. So thank you, Shankar, for all you've done, and thank you all for your time and attention.
Well, I just wanted to ask, this is working?
I can hear you.
Okay. your description of this fixed point thing sounded an awful lot like dynamic programming.
Yep.
Is that
Can they be related? Almost for sure. There's one thing is in the fixed point algorithm, there's not necessarily a cost function, right? So think of it more as a satisfiability thing in dynamic programming as opposed to also back property and cost. But you can imagine doing that, right? So maybe the way to say it would be if you wanted to do optimal correct by construction, so this would probably look a lot more like dynamic programming, cursor dimensionality, right? All of those sort of things. Yeah, I think that's right. So and dynamic programming can be done in discrete spaces. The one thing I would say here is you want to think about the reactivity of the environment as something that's not a traditional part of dynamic programming, right? The fact that I say, look, if the environment takes this action that pushes me out, I can take an action that pushes me, a little bit different. But I think conceptually you're right? Those are very similar approaches. You're back propagating sets, right, and looking for fixed point, whether you're doing a value iteration or a synthesis or a strategy iteration, right? Same types of ideas, yeah.
Yeah, Richard, I have two comments. I may have one comment and one question. The comment comes from being old, telling you that basically that notation really goes back to Kripke.
Yes, Kripke's cut structure, absolutely,
Okay.
right.
And he was in the 50s and maybe even 40s, and he comes from not mathematics, but philosophy and logic.
Ah, this I didn't know the history of that.
Okay?
Right.
He had some visiting positions here when Tarski was here.
Ah, no kidding.
Okay? So
And
that's...
so maybe to your earlier comment, we all build on the shoulders of others, right? And
right,
so, you know.
Right. So that was my comment. And, it really goes back to modal logic, to necessary and sufficient.
Yes.
The square was the necessary and sufficient was
The diamond.
diamond, okay? And then, actually, later on, my former advisor, John McCarthy, started the temporal logic and renamed these symbols to accommodate temporal. And Pnueli visited Stanford.
Ah, no kidding. I didn't know this either.
And picked it up, and then I interacted with him when he came to Penn. He was a visiting professor there. So
Yeah, I mean, it's a fantastic set of results, and there's a rich and wonderful literature out there to read about all this.
So that's the comment.
Yes.
The question I have is, which always I have been, the AI people, if I can come, the AI people, and that's why I got so excited about the combination of automata and continuous, is because they modeled walking, one state, another state, another state, and the combinatorics was obscene.
Yes.
Okay? So the question here, my friend, is how do you accommodate this? I like your simple scheme and then go back and back and back. How do you accommodate to optimize so that you have a flexible cells, side of cells, which is really subspaces? How do you do that?
Yeah.
Because that's the art.
Yes, good. Fantastic question. So let me say a couple of things. So, okay, so I've obviously, in a very short talk, hidden a lot of details under the rug, right? So let me tell you two tricks that will be familiar to everybody in the controls community that you want to use. So first off, I said it's cubic in the number of states, and so I say, great, plan your trajectory from here to the San Francisco airport, right? So what's the number of states, right? So the number of states is the possible location of every car you're going to meet along the way.
In 67.
Yeah.
Exactly the same problem.
Right. So the number of states is, the number of possible locations of every single car that you're going to see between here and there, cross-producted with every possible location you're in, cross-producted with every possible mode you're in. Are you texting, not texting, et cetera, et cetera, et cetera. This is ridiculously huge, and that cubed is ridiculously huge cubed, right? So you're not going to solve that problem, right? Okay, so we use two tricks, right, to sort of solve that problem. The first trick, receding horizon control. I don't need to solve the problem from here to San Francisco airport. I need to get outside the door. Right? And I'm going to assume that if I get outside the door in a reasonable way, some terminal cost, terminal set, something like that, I'll be able to find a path the rest of the way. Once I get outside the door, actually once I walk one step forward, I'll resolve the problem, right? Resolve. What have I done? So first off, I now know the location of everything. I don't have to worry about every car out there, et cetera. I only have to worry about you guys in this room. And Roberta's pretty quick, and Aaron I would worry about, so I'd probably go this way, right? And so, but that's it. I don't really have to worry too much about, right, everything else at this point, right? So it restricts the size of the problem tremendously, right? So and you can reset somehow, right?
Otherwise, you have these ad hoc thresholds.
Right.
Which
Yeah. So one is, to think about restricting the horizon and using this kind of counterintuitive point that sometimes you got to solve it online now, right? So sometimes it's a little bit counterintuitive. I'm taking an impossibly hard problem to solve offline. I'm going to solve it online better, right? But why? Because it's a much simpler problem to solve. That's one. The second is symmetry. Right? Not so much evident maybe in this room, but when I come up to an intersection, the intersection right at the corner down here, down the hill a little bit looks just like the intersection. Further down the hill looks just like, so it's just a symmetry, right? I can translate all these problems. I don't need to resolve the problem, right? I just need to flow forward the solution to the sort of the new location, right? So I can more or less cache previous solutions, right? And say, I recognize this situation. Maybe I have to apply a diffeomorphism because the streets are in some slightly different angle, but as long as that diffeomorphism doesn't break my trajectory generation underneath it, right? Sort of you can't turn too sharp. If it comes like this, right, it breaks. But I know how to, sort of do those things. So those are two tricks that we can use, right? That again, they're analogs, right, in the way that we do control systems. Linear systems work because they are symmetric problems. There's symmetry there, right, a translational symmetry that allows me to do things, right? So the same linear controller works no matter where I am because of the dilation that's present. So we have to apply those same tricks here. Work to be done. Yeah.
Okay, two more questions, Massimo and then Shankar.
So going back to Shankar's comment of organized hacking, maybe I could argue that a little bit of hacking, or call it engineering art, is always necessary. Because as you showed, you have a specification. A specification is up to the engineer.
Yep.
If you screw up the specification, you have an example, right? You have to go back and change it because it didn't make sense. So that part still can have errors, right?
Yeah, and I think it's the same as in every other engineering discipline. We could still be writing in assembly language if we wanted to, right? But we write in higher level languages because we can reason more easily, right? In something like Python or some, or CVXPy or something like that. Because now we've gotten the description up to something where we think we're probably on sort of more solid footing in terms of saying what we want. But you're right that absolutely there's still an art there, right? It is solving the problem you as a human tell it to solve, the engineer tells it to solve, and if you give it the wrong problem, it will blindly solve that problem and tell you there's a solution, right? And so we have to decide, do you want to write in assembly language or do you want to write in something higher level, right? The one thing I would tell you is you don't want to write in LTL, for sure, right? So you're going to put a higher level language on top of that too, right? A domain-specific language for your specifications that will compile to LTL, right? Because humans don't reason well about LTL, right? Just like assembly language, right?
Yeah, because sometimes people think that provably correct is the end of the story.
Oh, yeah, absolutely not. Right? We have to then go, and of course there's going to be, in some sense, you don't need to verify anymore, right? Because that part's automatically correct. But you need to validate, right? Does it actually solve the problem you want to solve? Does it solve in a real-world environment where the models don't necessarily match, right? Exactly what where the physical dynamics may or may not match my model perfectly. How do we deal with that? That's a robustness question, so we have to think about that just like we normally do.
So, I want to revise my 1988.
For the record.
So I say, nowadays, if you go to the average AI conference, I think it's no different from the average control conference in that there's boatloads of stochastic control, POM-DPs,
yep.
and just the language that we are. So, and here we are, just to follow your talk. So we are now looking at the formal methods and the provably correct. So what is the rapprochement now between sort of this probabilistic, the kinds of probabilistic guarantees, be they in cellular neural the deep learning, or in those learning, reinforcement learning, all of those, and sort of us going back and now computing fixed points of.
I think it's a great question. I'm going to answer that 10 years from now when we're here for your 70th birthday. And Claire can give me the talk title, and she just got to remember this is what it is. Good.
We'll use a French word.
Great. Thank you very much.